Good afternoon, and thanks for staying for the last paper talk at WIST 2018. I'm Xiaoyi Zhang from University of Washington, Dub Group, and Paul G. Allen School of Computer Science and Engineering. My main research focus is about mobile app accessibility, and today I would like to talk about robust annotation of mobile app UI, which can improve accessibility of mobile apps. This work is done with Annie Spencer-Ross and my advisor, James Fogarty. Among 7 billion people on this planet, more than 1 billion people live with some sort of disabilities. Mobile touchscreen devices and apps play increasingly important roles in daily life. In the US, 58% adults with disabilities use smartphones. However, not all of them are accessible. Last year, we examined top 100 free Android apps and found that every app included one or more categories of accessibility issues. In a follow-up study this year, we examined 5,000 Android apps for a specific category of accessibility issues. Almost half of these apps have more than 90% of their image button unlabeled. Yelp app is an example that is inaccessible for people with visual impairments, who mainly rely on audio feedback to use apps. When users touch this button, screen reader is supposed to rate 4 stars. However, Yelp developers used customized inaccessible widgets and didn't provide alternative text. Therefore, the screen reader cannot even select any star in the rating button, not to mention speaking the correct alternative text. At SIGCHI 2017, we present interaction proxies. It is a strategy to repair accessibility issues by third-party developers. One key method is to add an accessible overlay on top of inaccessible UI elements. In this case, when users touch the rating button, the screen reader will rate 4 stars from the overlay. Interaction proxies provide proof of concept repairs. We manually locate the element and add accessible metadata by writing code. It is easy to repair one issue as demonstration, but there are several problems in this in practice. After we repair a button in the screen of an Asian restaurant, we want that repair can also be applied to different restaurants. To reuse those repairs, we would like to have a more robust method to identify the different screens. Another problem is it is not practical to manually write an interaction proxy for each screen in each app. We need methods to make repairs scalable and reliable. In this work, we would like to enable annotation on mobile app UI, which improves the robustness and scalability concerns I just mentioned about interaction proxies. So here's the outline of my talk. We already introduced the mobile accessibility issues and potential repairs. We also find the problem in the previous repairs. They are not reliable or scalable. Our key contribution in this work is novel screen and element identifiers that enable annotation on mobile app UI. Finally, we will talk about evaluation and future opportunities. We learn from social annotation techniques that enhance web accessibility. There are 3 steps. A person observes and reports accessibility issue. That person or another person can annotate the interface with metadata. Finally, a tool uses the metadata to repair the issue. This method separates metadata and code. It makes the repair easy to scale, and the data can be shared or reused. In our previous work, one interaction proxy can only repair one UI element. We would like to examine whether we can support the same pipeline from social web annotation to make mobile accessibility repairs also scalable. In this example, we show the person detects an issue I just mentioned before. The screen reader cannot access the star rating button, and therefore, user cannot write reviews, which is a main feature of Yelp. We developed a tool to allow reporting accessibility issue by touching the bottom right button to upload the screen and the related metadata on that screen. Then a person can annotate the app with the correct metadata on our web interface. A person can define clickable areas for the reading buttons and provide labels for each of them on this interface. So finally, inaccurate proxies can use the annotation to repair the issue. Now the users can access reading buttons and write review.
3 stars, 4 stars.
Oh, sorry, I forgot to. So the key challenge here is to make identifiers that links each annotation metadata with the inaccessible UI element. We first need to identify the screen for annotation, and then identify the UI element on that screen. Again, we're inspired by web annotation, where URL can identify a page, and then XPath can identify UI elements on that page. However, there's no such standard identifiers on mobile platform. Therefore, we build our own identifiers for screen and UI element on mobile platform. So I would like first to go through how we did screen identification, which is a more challenging question, and it is our key contribution in this research. Therefore, I will focus on it for a while. We collect all screens we would like to annotate first. There can be duplicate screens from different paths we visit the app. For example, we have 3 screens of different restaurants in Yelp. We only want to keep one of the duplicates to create an annotation on it. We call unique screen as template and only create annotation on those templates. Now we have a template screen, database, and annotation on each template. When we apply annotation to repair a mobile app, we compare the current screen with each template in the database to find a match. When creating and applying annotation, we always need to check screen equivalence. That's why it is very important for annotation. To reuse annotation, we would like to define 2 screens with same UI structure as the same, even when their contents are different. Here we show the screen finds its match in the database, although they are from different restaurants. The method to determine screen equivalence may not be 100% correct, and we would like to minimize the errors. There are 2 types of errors. First, a false different error is when 2 screens are the same, but the system determines they are different. If this error happens, we cannot reuse the annotation. This error is not critical, but we have to spend more time to create duplicate annotation. There's also a false same error when the 2 screens are different, but the system determines they're the same. It is more critical because annotation on a screen may apply to a wrong screen, so we prioritize reducing this error. I would like to introduce 2 approaches to screen equivalence in previous research. They have motivations outside accessibility, but the pros and cons of their approaches inspired us. At last year's UIST, UIUC Data-Driven Design Group introduced the RICO, the largest repository of mobile app designs. Their motivation to compare screen equivalence is to avoid visiting the same screens. They compare 2 screens with view ID and screenshot, but they don't use much information from UI structure. However, not all elements have view ID, and also it requires screenshot permission on device. This method is quick and effective and fits the goal of RICO system. However, we would like to have less error for our annotation. The second project, DCAF, aims at detecting advertisement fraud in mobile apps. Their motivation is to determine if they cover enough screen in app by using screen equivalence. They compare 2 screens using cosine similarity matrix, which considers UI structure. However, their statistical method requires a larger number of screen data to manually tune the best parameter and threshold. Its error rate is too high for our annotation purpose. We have very different motivation from those previous research. For annotation, we care UI structure over content. If two screens share the same UI structure, our annotation can be reused on both screens. If their UI structure are different, we just have to treat them as different screens. One of our key insights is information exposed by UI elements. UI toolkits creates systematic errors of screen equivalence. You will see how we identify and reduce these errors in our evaluation later. Also, we use heuristics instead of statistical method, which doesn't require massive dataset. And our error rate is reduced for the annotation purpose. So in our evaluation of screen equivalence, we recruit 5 developers to collect more than 2,000 screens and provide ground truths of screen equivalence. In these 2,000 screens, there are more than 40,000 pairs of screens. We apply several heuristics to examine UI structure or other properties to reduce those errors. We first apply a baseline screen equivalence heuristic, which compares the set of UID property in a screen. However, only few elements have this optional property, and therefore there are some errors. We would like to reduce them. We first examine activity name. It is so an app can contain several activities for major features. Checking this reduce false same error. If two screens do not have the same activity name, then they're not the same screen, even if they're recognized as the same by the first heuristic. As I mentioned before, UI structure is one key factor that we should consider. It may introduce errors systematically. Here are some UI structures that cause false different errors. So there can be navigation drawer or floating dialog. When they are open, user cannot interact with the content beneath it. So we should only consider the top level content. So in this example, if we annotate the yellow button on the left side, the yellow button on the right side should also be applied the same annotation, even if the content beneath the navigation drawer are different. We then can also examine UI structures that introduce false same error. There are tab layout, radio button layout, and also other UI structure that may expose all content to accessibility API, even when some content are out of screen or not fully rendered. But we should only consider the visible content for our annotation purpose. Therefore, if two screens expose the same content, but they're in a different tab or different radio button, or have different visible content, we should treat them as different screens. Finally, we compare the set of class name in screen. Class name indicates the category of our UI element, like image button or view or image view. Applying this heuristic can decrease false same error, but it increases the first different error a little bit. We also explain some ways to further reduce this error in our paper. So as a result, after applying all 8 heuristics, we reduce 97% of false same error and 60% false different error. We prioritize false same reduction in order to avoid applying annotation to a wrong screen, which is a more critical error. So I just explained how we identify a screen in an app, which is a more challenging problem. In comparison, element identification is relatively straightforward, as we simply extend techniques in Android testing framework with XPath and selector. We also extend new properties in selectors, which you can read the details in our paper. So for different issues, we create different annotation, which is annotation. We define this as an association between metadata and those inaccessible UI elements. In our paper, we designed 3 annotation web interfaces and data structure for 3 different accessibility issues. Developers can modify our example code to create new annotation for additional issues. So in our evaluation, we focus less on how effective the repair is, because we already did this in our previous paper. But this time, we are focusing on the feasibility of a robust and scalable annotation to enable accessibility repairs. So in first study, we interviewed a blind person who used TalkBack for 6 years. He identifies accessibility issues in 6 daily used apps. We repaired around 40 issues in these apps with our annotation system in an hour. After he learned our approach and experienced the repairs, he provided positive feedback as those annotations quickly solved most of his issues. We also noticed and discussed a small fraction of issues we couldn't repair. If you're interested, please read our paper for details. We also repaired additional apps to validate our method at a larger scale. 4 categories of accessibility issues in 26 apps are repaired with our tools. Compared to our proof of concept in action proxies, this annotation repairs more accessibility issues and takes less time for each, thereby supporting the potential of annotation-based accessibility repair. In the future, we would like to build a crowd-source-based system to annotate the mobile apps to repair accessibility issues at scale. So it shouldn't be limited to only 26 apps we evaluated, but maybe for thousands of apps. Secondly, we can use additional screen data to improve our heuristics. And we also would like to repair additional types of accessibility issues. Finally, we would like to open source the project and see our work to be used by research outside accessibility. For example, in UI automation research. In summary, the robust app UI annotation makes accessibility repairs more reliable and scalable. In our previous work in action proxies, it allows customization in a specific app. In this work, annotation allows enhancement on a specific screen. And lastly, with our screen equivalence heuristics, we reduce a large portion of screen identification error, which may also be applied to additional research. So thank you. I would like to take your questions, and then we can enjoy a coffee break. Thank you.
Great. So we'll take questions. I've got a first one right here in the front.
Hi, Ranjita Kumar, UIUC. Great talk. I had a question about how your repairs carry over to situations where the app gets updated. So if someone goes into that Yelp screen and adds another element, will that be now a different screen? So you would have to redo the repair?
Yeah, thanks. It's a great question. And also thank you for your previous research, which inspired our research. So yes, it's a great question. And to answer your question, if an app updates, it may or may not have to be updated as its UI the UI structure may not change. Maybe only the slide content change, but not the whole UI structure. Maybe the button may increase 20%, but the whole UI structure is still the same. In that case, we don't have to update our database. However, if there's a major update, for example, in Yelp, they experienced a major update, I think, earlier this year. In that case, we have to update our database to satisfy the new design. Yeah, thank you. And I think in the future, one of our future work is how we maintain those kind of database based on the version and also based on the UI change. Thank you.
So we have time for just only one more question, and I'll give it to Rico there. Or Tico, sorry.
Yeah, no problem. Hi, Tico Bayagas from HP Labs. Nice work. I didn't understand exactly how the system gets around issues around different display sizes and adaptive layout and portrait versus landscape. Can you explain that more clearly?
Yeah, thank you. It's another great question. So the first part is it is similar to the updates, the different versions. We also So the landscape and portrait mode are definitely two different UI layouts. So we have to maintain for both orientation. And I think for other cases, sometimes it may be like different UI structure, sometimes it's not. So it's still based on if the UI structure are the same or not. And similarly, we may also want to maintain a database on different version, different orientation, and different other properties, like different screen sizes in our future research to maintain those kind of database. Thank you.
Great. So just some, let's thank our speaker one more time. Just